Yeah.
Um, Hi, everyone. It's my great pleasure to introduce John Williamson as the next speaker in our seminar series. John is a professor of philosophy at Manchester University. I have personally had the privilege of working with and learning from John for many years now. He's a great logician and a philosopher with outstanding contributions to inductive logic and probably the most prominent advocate of the objective Bayesian account. Today, John will talk to us about the limits of standard conditionalization and what that means for the Bayesians. John, thank you very much for joining us, and the floor is yours.
Thank you very much. It's a great pleasure to come and talk. So thank you for inviting me here. Okay, so I'm going to be talking about Bayesian conditionalization, standard Bayesian conditionalization. I'm going to introduce conditionalization and limits to its use. So I'm going to argue that Bayesian conditionalization shouldn't be advocated as a universal principle, but it only holds in some situations and not others. So the question arises as to how we should understand the limits of conditionalization. So we need some fairly broad framework within which we can understand when Bayesian conditionalization is appropriate and when it's inappropriate. And I'm going to introduce objective Bayesian inductive logic, which is going to provide that broad framework for conditionalization in section 2. In section 3, I'm going to talk about, from the point of view of objective Bayesian inductive logic, when conditionalization holds and when it is inappropriate. And then I'm going to explore some consequences of these results for Bayesianism in general. I should say that some of the work in section 1 draws on joint work with Christian Wallmann, and section 2, objective Bayesian inductive logic, is a joint project with Sarouche and also with Jürgen Landes. So that's all joint work as well. Okay, so first of all, Bayesian conditionalization. So I'm going to consider a belief function B sub E of A being the degree to which you'd believe proposition A, given just E, proposition E. And I'm going to assume that this is defined for all propositions in the domain A and E. Now, standardly, Bayesianism assumes that conditional beliefs, so B sub E of A is a conditional belief function, that conditional beliefs are conditional probabilities. So this can be cast as the principle for any rationally permissible belief function B, there's some probability function P such that B sub E of A equals probability of A given E for all A and E. So this says that your conditional belief function is actually a conditional probability function. And Bayesian conditionalization builds on this sort of core tenet of Bayesianism. You can think of Bayesian conditionalization as CBCP together with the view that your actual current beliefs are conditional beliefs. So your for any time t, your degrees of belief at t are the values encapsulated in the belief function B sub E, where E is your total evidence at t. So putting these two principles together, you get Bayesian conditionalization. There's some probability function P, such that for any time t, your degrees of belief at t are the conditional probabilities conditional on E, where E is your total evidence at t. So the idea is that Bayesianism as a whole assumes CBCP, conditional beliefs are conditional probabilities. Add that with the principle that your current beliefs are actually beliefs conditional on your current evidence, and you get Bayesian conditionalization, which is the principle that your beliefs should track your evidence using conditional probabilities. Now, Bayesian conditionalization has got a bit of a mixed history. So on the one hand, CBCP is absolutely core to almost all versions of Bayesianism, and Bayesian conditionalization tends to be viewed as either a crucial principle for Bayesianism, or even something constitutive of Bayesianism. You're not a Bayesian unless you conditionalize. So the dominant view is that Bayesian conditionalization is absolutely central to Bayesianism. Some authors have objected to this view. For example, Henry Kaiberg, Colin Howson as well had some objections, and I've listed a few objectors there. I'm also going to put forward an objection, but it's slightly different to these ones already in the literature. So here is an objection to the universality of Bayesian conditionalization. In fact, this is an objection to CBCP, the view that conditional beliefs are conditional probabilities. So remember, that's usually taken to be absolutely core to Bayesianism. So here's the example. You have a fair six-sided die that needs to be rolled. That's proposition X. And each face of the die is colored red, blue, or green. That's your proposition E. The number rolled will be 3 or greater. That's an outcome you're interested in, outcome A. And the color rolled will be red. That's another outcome we're interested in, outcome R. Now, I'm going to assume conditional beliefs are conditional probabilities. So I'm going to think in terms of conditional probabilities here. Given this example, it seems obviously rationally permissible to set one's degree of belief in A, that the outcome will be 3 or greater, to be 2/3, given evidence X and E. Why is that rationally permissible? Well, there are 4 outcomes greater than or equal to 3, outcome 3, 4, 5, and 6, and each number has a chance of 1/6 being rolled because the die is fair. So it seems obviously rationally permissible to believe A to degree 2/3. It seems also obviously rationally permissible to believe that the face of the die, the color rolled, the color of the uppermost face will be red to degree 1/3. Why is this? Well, there are 3 possible colors. It could be red, blue, or green. So there's no evidence that favors one of these 3 colors over any of the others. So it seems reasonable, at least permissible, to believe that the outcome will be red to degree 1/3. Now, suppose you learn that the red faces are exactly those that are numbered 3 or greater. So this can be expressed as A if and only if R. It seems still reasonable to believe the outcome that the number rolled will be 3 or more to degree of belief 2/3. Why is that reasonable? Well, for the same reason as it was before learning this new information, that there are 4 possible outcomes that fit A, and each of those has probability 1/6. And it seems also reasonable to suppose that these conditional probabilities are all well defined, so that the thing that you're conditioning on has non-zero probability. So the probability that the red faces are precisely those numbered 3 or more has that probability is greater than 0. So these seem kind of, in this example, 4 obviously rationally permissible degrees of belief. The problem that Bayesianism faces is these assignments of probability are inconsistent. So take 3 of them. So this is degree of belief in A is 2/3, degree of belief in R is 1/3, and that the conditional probabilities are well defined. Then you can show that degree of belief in A, after learning that the red faces are precisely those that have numbers 3 or greater, that probability must be a half. and can't be 2/3 as we argued it ought to be in the first place. I'm not going to go through this now, but we can talk about this in the question time if you like. But the point is that when you learn this new information, you have to update your degrees of belief to a half in A, and you can't keep degree of belief 2/3, even though 2/3 is obviously the chance of A being true. So we had 4 claims about rational permissibility of conditional beliefs. These seem to be kind of obviously true claims, but we couldn't use conditional probabilities to validate these facts about rational permissibility because they're inconsistent. So we had 4 inconsistent claims when you couch them in terms of conditional probabilities. What's the conclusion? The conclusion is that conditional beliefs aren't always identifiable with conditional probabilities because these are facts about rational permissibility when it comes to conditional beliefs, but they're not validatable using conditional probabilities. Bayesian conditionalization depends on the identification between conditional beliefs and conditional probabilities, so it can't hold universally. Here's an example in which it doesn't hold. So it can't hold universally. So the upshot is conditionalization is best thought of as a heuristic. So it's convenient to use in a broad range of situations, but it leads to error in others. You can't use it safely in every situation. And here's a simple example in which you can't use conditionalization safely. It gives you the wrong answer. So then the question arises, if you're viewing conditionalization as a heuristic principle rather than as a universal principle that's constitutive of Bayesianism, the question arises, when is it safe to conditionalize? When is it okay to use conditionalization? And when should we not use conditionalization? And to answer this question, we're going to have to appeal to some broader framework for handling rational degrees of belief, so that we can ask in that broader framework when conditionalization holds and when it doesn't hold. And the framework I'm going to talk about is objective Bayesian inductive logic. So I'm going to move on now to talk about objective Bayesian inductive logic. I'm going to take a bit of time to explore what this framework is, and then later on in the talk we'll return to the example and talk about when conditionalization holds and when it doesn't. So objective Bayesian inductive logic appeals to the principles of objective Bayesianism, and you can understand objective Bayesianism as imposing 3 kinds of norm on strength of belief. There's a structural norm or constraint that degrees of belief should satisfy the laws of probability. So, for example, they should be additive. The degree to which you believe that the next card to be drawn from a stack of playing cards will be black should be the sum of the degree to which you believe it's a spade and the degree to which you believe it is a club, because those are the black suits. The second kind of norm is an evidential norm on degree of belief. So degrees of belief should satisfy constraints imposed by evidence. And in particular, they should be calibrated to empirical probabilities insofar as you have evidence of them. So, for example, you should believe to degree a quarter that the next card drawn will be a club in your standard pack of cards, because the chance of it being drawn is a quarter. 25% of the cards are clubs. And the third kind of norm is an equivocation norm, that your degrees of belief should otherwise equivocate as far as possible between the basic outcomes. You shouldn't be committal about one outcome occurring unless you've got evidence that that outcome will occur. So you should be non-committal with respect to the basic outcomes if you don't have evidence that favors one outcome over another. So if you know that an experiment only has 4 mutually exclusive outcomes, A, B, C, and D, and you know that A has empirical probability 0.1, that means B, C, and D, you've got to be given probability 0.9 between them. If that's all you know, then you should believe the next outcome will be outcome B to degree 0.3, because you're splitting 0.9 probability equally amongst 3 different outcomes. And this is related to the Laplace's principle of indifference. So all Bayesians are happy with the structural norm. Degrees of belief should satisfy the laws of probability. Virtually all philosophical Bayesians, at least, are happy with the evidential norm, that degrees of belief should satisfy constraints imposed by evidence, and they should be calibrated to empirical probabilities. What picks out objective Bayesianism from subjective Bayesianism is this equivocation norm. So many subjectivists would reject the idea that you should equivocate between basic outcomes. Objectivists, on the other hand, would endorse this idea. The maximum entropy principle, due to Edwin James, has been put forward as a natural way to explicate the equivocation norm. Entropy, Shannon entropy, is a measure of the extent to which a probability function equivocates between basic outcomes. And so the maximum entropy principle says, select the probability function that has maximum entropy from all those that satisfy the constraints imposed by the evidential norm. This works quite well when the space of basic possibilities is finite. So if you've got a finite domain, this works very nicely. But there is a philosophical problem, namely that the choice of your finite domain may be rather arbitrary, and you're going to get different answers, different probabilities, if you choose a different finite space to represent the same domain. And this would undermine the objectivity of objective Bayesianism. If you try and capture the domain in different ways and get different answers, then perhaps your probabilities are less objective than you might like. Here's a way out of that problem. You take your space of basic possibilities to be the basic possibilities expressible in your language. And then it doesn't matter so much that inferences depend upon the underlying language, because languages evolve to represent and reason about the world efficiently and can be thought of as providing implicit evidence about the world. And that some languages are obviously better than others at capturing the basic categories in the world. And so it's not so much of a problem if there's this sort of language relativity. Then the question arises, if you're going to take this linguistic approach to the problem, are we okay relying on a finite language, a finite space of basic outcomes? Typically, you're going to need at least the richness of a first-order predicate language to express many of the propositions that feature in our inferences. And so the concern then is that a finite domain or finite language is rather limiting. So let's try moving to a first-order language, but then we don't have a finite set of states, finite set of basic outcomes, finite set of possible worlds, and it's no longer obvious as to how you'd maximize entropy. So this linguistic approach perhaps solves the philosophical problem, but introduces a technical problem. How do you maximize entropy when your language is a first-order predicate language? And this is where objective Bayesian inductive logic comes in, because it allows us to solve this technical problem. So to say how to maximize entropy. So here's the basic framework. We're going to consider entailment relationships of this form. So the premise is phi1 has probability in x1, up to phi k has probability in xk. This partially entails a conclusion psi to the extent that it means that the probability of psi lies within the set Y. So that these are going to be the basic entailment relationships, inductive entailment relationships that we consider. Phi1 to phi k and psi are sentences of a first-order predicate language. X1 to xk and y are intervals of probabilities. And what objective Bayesian inductive logic is going to say is that the conclusion follows just when each maximally equivocal probability function from all those that satisfy the premises also satisfies the conclusion. So you can think of models of the premises as being maximally equivocal probability functions. And if every model that satisfies the premises also satisfies the conclusion, then the inductive entailment relationship holds. That's the basic idea of objective Bayesian inductive logic. Just to be a bit more explicit, we're going to consider a first-order language L that has relation symbols U1 to UL, constant symbols infinitely many T1, T2, and so on. We're going to be particularly interested in finite sublanguages that just involve the constants T1 to Tn. So these will have finitely many atomic sentences, and each finite sublanguage will have finitely many state descriptions, which we call n states. So these are the states of the atomic sentences A1 to ARn. X1 to xk and y are intervals of probability, as I mentioned. I'm not going to go into this, but these are the axioms of probability as defined over a first-order language. So the important thing to note is that the probability of an existential statement is supremum of the probabilities of disjunctions. And similarly, the probability of a universally quantified statement is the infimum. So we're going to take the premises on the left-hand side of the entailment relationship. So remember, we've got x1, phi1, x1 up to phi k, xk. Those are the premises. These are, we're going to interpret those as capturing all the evidential constraints, so all the constraints on rational degrees of belief that are imposed by our evidence. And we're going to consider the set E of all probability functions that satisfy these evidential constraints. And sometimes we're going to use blackboard P of phi1, x1 up to phi k, xk to represent the set of probability functions that satisfy these premises. Now, we can consider the Shannon entropy on each finite sublanguage, and we call this n entropy. So the n entropy of a probability function P is defined as the Shannon entropy of P on the language Ln. So remember, the language Ln just has constants T1 to Tn. And we take the n states, so the states of the atomic propositions of the language, and we define the Shannon entropy using those n states. But now, once we've got the Shannon entropy on each finite sublanguage, we can talk about whether one probability function P has greater entropy than another Q on the language as a whole. And we can say that P has greater entropy than Q if the entropy of P eventually dominates that of Q. So there's some stage after which the n entropy of P is strictly greater than the n entropy of Q. So for sufficiently large sublanguages, finite sublanguages, the Shannon entropy of P is going to be greater than the Shannon entropy of Q. If that holds, then we say P has greater entropy on the language as a whole. Now we can extend the maximal entropy principle to first-order predicate language. We say we use the probability functions that have maximal entropy amongst all those that satisfy the constraints imposed by the evidence. So we get a partial order here on the greater entropy relation, and we choose the maximal element. So we choose the functions that from all those that satisfy the premises, such that they aren't dominated by other functions. So these are maximal entropy probability functions. And then we say that the inductive entailment relationship holds just when probability of psi is in Y for every probability function that satisfies the premises and has maximal entropy. Okay. So that's the basic definition of objective Bayesian inductive logic. Just going to mention here that a particularly important case is the one where there isn't any premises. In that case, the maximal entropy function is just going to be the probability function that gives each n state the same probability for every n. And this is called the equivocator function, p equals. It basically gives divides the probability equally amongst every n state. This equivocator function is analogous to Lebesgue measure in kind of standard mathematical theory of probability. So we call the measure of proposition psi to be the value that the equivocator function gives that proposition. We can now consider what we call inductive tautologies. These are the propositions that get given measure 1. Inductive contradictions are the propositions that have measure 0. And we can say two sentences are inductively consistent if their consistency has measure 1, or an alternative way of putting it is that the negation of the conjunction doesn't have measure 0. And an interesting fact is that if for any sentence, if it's got no constants in it, then it must be an inductive tautology or an inductive contradiction. So that's the case in which you have no premises. Now I'm going to move on to a couple of cases in which we know that you're bound to have a unique maximal entropy function. So in these cases, inference in the logic is particularly straightforward because we only have to consider one probability function, one model of the premises, basically. So the first such situation is when the set of probability functions that satisfy the premises has finitely generated consequences. So you can think of two possible cases here. This set of probability functions that satisfy the premises E, we're going to call finitely generated if there are quantifier-free sentences that can be substituted for the premises. So the set of probability functions E that satisfy the premises is the same as the set of probability functions that satisfy these other premises with that are quantifier-free. So then what we want to say is that this set E is finitely generated. If E is not finitely generated, perhaps, but has finitely generated consequences, what do we mean by that? Well, there exist quantifier-free sentences such that the maximal entropy functions in E are the maximal entropy functions in this set of probability functions that satisfy the quantifier-free versions. And the quantifier-free statements are called generating statements for the consequences of E. So one case is when E itself is finitely generated, and another case is when maxent E is finitely generated. And so this is a slightly more general case. The key result here is that if E is closed and has finitely generated consequences, then it contains a unique maximal entropy function. We're going to call this P dagger. So in this case, this is the single probability function that satisfies the premises and is maximally equivocal. And we can characterize P dagger as follows. You take some n large enough that you can express the generating statements in ln, and then you can consider the n entropy maximizer on ln. So this is the standard Shannon entropy maximizer. And that's going to be unique on ln. And then you extend this n entropy maximizer to the language as a whole by just equivocating elsewhere. So you make the function p dagger be equivocal, maximally equivocal elsewhere. The point I want to emphasize here is that it's fairly straightforward to do this. You can use numerical optimization techniques or perhaps probabilistic graphical models to reduce the dimensionality of the problem, and you can fairly easily calculate Pn dagger. And in general, we know that the class of inferences whose premises have finitely generated consequences, that class is decidable. So this is perhaps a surprising fact, is that there's a large class of inferences that is decidable here in this inductive logic. I'm now going to introduce a concept called support satisfiability. So consider some sentence phi of L, of your language L, and consider the states of the atomic propositions that appear in that sentence phi. We're going to call the support phi check to be the disjunction of states that are inductively consistent with phi. So phi check is the disjunction of the states of the atomic propositions that occur in phi that have positive measure when taken together with phi itself. So you can think of the support as some kind of quantifier-free version of the sentence that has positive measure. So, for example, if you have a quantified statement, there exists x such that u of t1 and v of t1 and x holds, so v is a relation here, then phi check is just going to be u of t1 in this example. So when you move from a sentence to its support, you always end up with a quantifier-free statement. And we say that E itself, so the set of probability functions that satisfy the premises, is support satisfiable if this set of probability functions of the support that satisfy the supports is non-empty. So if when you replace each premise by its support, then there's some probability function that satisfies all the premises. And in many cases, quite complex premises, you're going to have support satisfiability, but there's some cases where your premises aren't going to be support satisfiable because they, in these cases, the premise sentences have measure 0. So these aren't support satisfiable. Okay, so the key result here is that if E is support satisfiable, then it has finitely generated consequences and vice versa. And these supports are the generating statements. So we now know exactly when a set of premises has finitely generated consequences, and it's when those premises are support satisfiable, when their supports are satisfiable. So we understand this situation quite well in objective Bayesian inductive logic, and we know that in this case, when you have satisfiable support, you have a unique maximal entropy function, and that this class of inferences that have satisfiable support, this is a decidable class of inferences. There's another class of inferences which you're guaranteed uniqueness in. I'm not going to go into this in any detail, but there's another concept called closure in entropy. And with closure in entropy, that allows us to deal with some of the statements that we couldn't deal with using satisfiable support. So, for example, universal statements, we get closure in entropy, even though we don't get satisfiable support. And the key situation is, even if you don't have support satisfiability, but you have closure in entropy, then you're still guaranteed to have a unique maximal entropy function. So these are two central cases for objective Bayesian inductive logic that are pretty well understood and where you're guaranteed to have uniqueness in the maximal entropy function. We don't know very much about what happens outside of these cases. So there are lots of interesting open problems and questions about whether outside these cases you still have unique entropy maximizers. I'll just talk briefly about relationship to another approach to inductive logic. Most famous approach is probably Carnap's approach to inductive logic, and then I'll go back to the connection with subjective Bayesianism and Bayesian conditionalization. Okay, so with Carnap's approach, Carnap considers categorical sentences. So these sentences don't have probabilities attached to them. And he has a continuum of inductive logics that are parameterized by a parameter lambda that is a number between 0 and infinity. And he's particularly interested in the probability of the conclusion statement given a sample of previous observed outcomes. So, for example, if you've got a sample of u's, your predicate u, and you're interested in whether a new constant will satisfy u, you can calculate the probability that your next observed instance is a u, depending on the proportion of the previous observed instances being a u. And this probability is determined by the parameter lambda. So it's the number of observed u's plus lambda over 2 divided by k plus lambda. So there's some differences between objective Bayesian inductive logic and Carnap's approach. So objective Bayesian inductive logic is rather more general because we don't just have categorical premises. We have premises that have probabilities attached to them. Carnap's approach requires some choice of lambda. He didn't talk much about how you determine lambda other than by saying it's sort of pragmatically determined. So this leaves some underdetermination, arguably. We don't really know exactly how to choose lambda. Carnap's approach tries to capture learning from experience within the logic. So he tries to say, when you've got experience of a past sample, what probability you should attach to the next instance. The smaller the value of lambda, the greater the influence of the sample frequency. He develops an approach which is based on exchangeability. The problem is exchangeability, again, is not a universal principle. I mean, exchangeability is sometimes appropriate. In other situations, it's not appropriate. So he develops an approach that arguably uses overuses heuristic, namely exchangeability. In objective Bayesian inductive logic, we consider the influence of the sample to be outside of the logic. It's not a logical question. What we want to do is we want to distinguish knowledge representation, so formulating suitable premises, from reasoning or entailment in inductive logic, and we take the influence of sampling and statistics to be part of knowledge representation rather than part of inference within the logic itself. So the general approach is, if you've got a sample of outcomes, you consider the narrowest confidence interval within which you infer that the empirical probability of a positive outcome lies. So, for example, if you observe 100 ravens and find them all to be black, then your confidence interval for the next raven being black is going to be something close to 1. And you use kind of frequentist statistics to infer that the chance of the next raven being black is going to be close to 1. And then you add that to your list of premises, because if you remember, the evidential norm says that you need to calibrate your degrees of belief to empirical chances. And so you would add that to your list of premises. So you have a new constraint here. And then that will give you a probability for, you choose a maximal entropy function that satisfies all the premises. That gives you a probability for the conclusion statement. So the statistics is going on here in formulating suitable premises. It's not within the inference machinery of the logic itself. So that's a major difference between objective Bayesian inductive logic and Carnap's approach. Okay, let's go back to subjective Bayesianism. So there are two kinds of subjective Bayesianism. There's the precise approach, which says the probability you attach to the conclusion is just a conditional probability of the conclusion on the premises. And an imprecise approach, which says that the premises partially entail a conclusion just if for any probability function that satisfies the premises, the probability of the conclusion given the premises is in that set Y. Problem with the precise approach is, again, you have kind of radical undetermination because you need to choose a prior, and there's no kind of normative reasons for choosing one prior over any other. The difficulty with the imprecise approach is it leads to a rather weak logic. It's often the case that the most you can infer from premises is that the probability of the conclusion sentence lies in the unit interval. So you don't have very strong or useful conclusions there. So the key difference between objective Bayesian inductive logic and these approaches concerns conditional probabilities. As I mentioned, conditional probabilities are absolutely central to subjective Bayesianism because you take evidence into account by conditionalizing. But conditional probabilities are of no special significance to objective Bayesianism. Why is this? Well, you take new evidence into account by calibrating to empirical probabilities again and applying the maximal entropy principle all over again. So there's no updating rule in objective Bayesianism. There's no rule that is conditionalization or an analog of conditionalization. All you do is you apply the maximal entropy principle each time your evidence changes, and that gets you a new probability function. And then you use that new probability function for inference. So in particular, this principle CBCP, that conditional beliefs are conditional probabilities, that plays no role at all in objective Bayesianism because conditional probabilities aren't of particular interest in objective Bayesianism. Instead, you have an analog that says that conditional beliefs are probabilities, but not necessarily conditional probabilities. So for any rationally permissible belief function, B and any E, there's some probability function that your conditional beliefs are that probability function. But this isn't necessarily a conditional probability function. So it has a very different role for conditional probabilities than the standard orthodox Bayesian account. And this brings us back to our starting point, the scope of conditionalization. And what I want to do now in this section is to use objective Bayesian inductive logic to tell us when conditionalization is appropriate and when it's inappropriate. You need one definition here. A new sentence, theta is simple with respect to the premises if it can be accommodated by simply adding the constraint that the probability of theta is 1 to that background of the premises. So if learning theta in the presence of the premises can just be explicated by adding theta as a new categorical premise. So your new set of premises is your old set plus the statement that theta has probability 1. That, in that case, theta is called simple. And here's the main result. So suppose B is your set of premises, and this determines some set E of probability functions that satisfy the premises. You've got some maximal entropy function P dagger. And then you learn some quantifier free statement theta, and you get some new set of probability functions E prime that satisfies the old constraints plus the constraints imposed by theta. If 4 conditions hold, then P dagger conditionalized on theta is going to be in the new set of maximal entropy functions. So basically it's safe to conditionalize on theta from the point of view of objective Bayesian inductive logic. So this result says that you're guaranteed that your conditional probability function is going to have maximal entropy with respect to the new constraints. What are the 4 conditions? One is that theta is simple, so it can be captured. Learning theta can be captured just by the constraint probability of theta is 1. The second condition is that the original maximal entropy function must give positive probability to theta. So you can't safely conditionalize if theta has 0 probability. The new probability function the old probability function conditionalized on theta must also satisfy the old constraints. That's the third condition. And the fourth one is that if the negation of theta has positive probability, then the probability function conditional on the negation of theta also satisfies the old constraint. So if these 4 conditions are satisfied, then it's safe to conditionalize. And we know that in many situations, so for example, if B has satisfiable support, then you're going to have a unique entropy maximizer. So the conditional probability is going to be the unique entropy maximizer there. So it's uniquely rational to conditionalize in those situations. Importantly, if one of those 4 conditions fail, then you shouldn't conditionalize. So for example, if theta is not simple, then you shouldn't conditionalize. Why? Because if theta is not simple, then either theta conflicts with and overrides some of the old constraints, or it has complex consequences that can't be captured by simply adding theta to the old constraints. We have an example of this. Suppose there are no old constraints, but theta says 100 ravens have been sampled and all found to be black. as I mentioned, this is going to determine a confidence interval for the next raven being black that's going to be close to 1. And you arguably theta, that evidence imposes a constraint that your probabilities for future ravens being black should be close to 1. But it's not safe to conditionalize, because conditional probability function, you're going to have the equivocator function initially, and the equivocator function gives conditional probability a half to the next raven being black. So it's not safe to conditionalize in that situation. If theta has probability 0, it's not going to be safe to conditionalize, and this is kind of well known that you can't conditionalize sensibly on statements that have probability 0. If the conditional probability function isn't in E, doesn't satisfy the old constraints, then again, it's not going to be safe because the old constraints need to be satisfied. And if learning the falsity of theta wouldn't satisfy the old constraints as well, then arguably it's not going to be safe to conditionalize. So these were our 4 conditions on when it's safe to conditionalize. So let's go back to the red faces example. These were the conditional probabilities that we'd like to all hold, and we found that these are inconsistent. These don't all hold together. How would objective Bayesianism deal with this situation? Well, here your old evidence B is X and E together, and the new proposition you're learning is A if and only if R. And it turns out that condition 1 fails. Theta is not simple with respect to B, and condition 3 fails. The new conditional probability function doesn't satisfy the old constraints. Why does condition 1 fail? Well, because via the evidential norm, we know the chance of A. The chance of A is 2/3. So we've got this extra constraint. The chance of A is 2/3. And learning that A is equivalent to R isn't going to be captured just by adding A if and only if R to E. Condition 3 fails because we saw from the proof given earlier that X and E together imposes the constraint that probability of A is 2/3, but we saw that actually the conditional probability is going to be a half. So that disagrees, that fails to satisfy the constraints imposed by evidence. So the answer is objective Bayesian inductive logic would say it's not safe to conditionalize in this situation. Instead, objective Bayesian inductive logic would handle this situation by using regular probability functions, not conditional probability functions. So it's going to ask what probability function in E has maximal entropy. And it turns out the probability function in E that has maximal entropy gives A probability 2/3 and R probability 1/3. And then on learning A if and only if R, we need to find the probability function in this increased set of propositions that has maximal entropy. And in fact, that picks out a unique probability function. And again, we get probability of A is 2/3. So this is exactly what we wanted, that fitted our intuitions about rational permissibility there. So objective Bayesian inductive logic can capture those, can validate those rational permissibility statements that we started off with. We only have a problem if we insist on conditionalizing. Okay, I'm going to skip a couple of corollaries and then go on to the final consequences of the talk. So I've argued that conditionalization is a useful heuristic, but it's not universally valid. It can lead to error in pathological situations, and we know that those pathological situations are captured by those in which the conditions of our theorem are violated. So what are the consequences of this? First of all, conditionalization should not be thought of as constitutive of Bayesianism. So we shouldn't say to be a Bayesian, you need to conditionalize, or to be a Bayesian, you need to take conditional beliefs to be conditional probabilities. That's not going to work because we know that CBCP and Bayesian conditionalization don't hold generally. Instead, we might understand more Bayesianism in a more general way as any theory that identifies rational degrees of belief and probabilities. So if you have a Bayesian interpretation of probability, then you're construing probabilities as rational degrees of belief. In the other direction, Bayesian epistemology construes rational degrees of belief as probabilities. We shouldn't be giving any special emphasis to conditional probabilities here. Secondly, objective Bayesianism doesn't need to presuppose a separate updating principle such as conditionalization, because the maximum entropy principle can handle updating all by itself. So you don't need any updating principle if you're an objective Bayesian. Thirdly, subjective Bayesianism, which rejects the maximal entropy principle, now faces a problem. Subjective Bayesianism needs conditionalization because it doesn't have an independent means of accommodating new information. So with objective Bayesianism, you can just use the maximum entropy principle to accommodate new information. You can't do that with subjective information. You need some kind of updating principle. What updating principle? Well, subjectivists will say conditionalization. But conditionalization isn't universally valid. So this means that subjectivism is at best a partial account of inductive inference. It tells us, it appeals to a heuristic that works sometimes, but it doesn't tell us what to do when it doesn't work, and it doesn't tell us when it doesn't work. I think the same lessons carry through to what's called the new paradigm in the psychology of reasoning. So the new paradigm approach to the psychology of reasoning seeks to understand our reasoning by appeal to conditional probabilities and conditionalization. So, for example, it analyzes our use of conditionals in language in terms of conditional probabilities. So it invokes conditional probabilities to understand conditionals. I don't think that's going to work in general because the CBCP fails in general. It works at best as a heuristic. So if the new paradigm is going to account for the heuristic role of conditionalization and its failure in pathological situations, then it needs to move to a more general framework, such as objective Bayesian inductive logic. Okay, thank you very much. I'm going to draw to a close there and look forward to your questions. Thanks a lot.
Thanks a lot.